I want your help a little bit because on next week British is teaching, and I want you to show him how this works. So 1 second. So basically, it's not a big deal, but still, you would just need to know how to. Well, that's the easy part. But then what he needs to know is this. So you do this, and we can start with A. Once you connect it to the laptop, this should go down. Once it's down, do the same thing for B. Basically, you do B, and I'll show you in a second. When you go to B, it moves back to the PC.
Okay.
Let's see. And then go again to laptop, so it will go. And then the other thing is the light. So the light I do 2.
Okay.
2 is the good one. Okay. So if he, I'll tell him that you know. Thanks. Oh, one other thing actually. One other thing. He needs the mic. The mic is already here, loaded. He just needs to connect it and turn it on. Okay, so let's start. So I'm hoping you all recovered from the midterm. We're going to talk about it next time. Hopefully everything will be graded before the end of this week. So we're starting with a new topic, support vector machines. Before we get there, couple of administrative things. So next week I'll be away. Someone else will teach the 2 lectures. There's some echo. Can you hear me well there? Okay. So no office hours, but the 2 weeks after that, 11 and 18, I'm planning to try to talk to all the people that are doing projects. So we have 40 projects, it's a lot. So please start working if you are doing a project. Don't wait. You will get comments this week, brief comments on the proposals. I'm sure you will change your mind regardless of the comments, just when you start working on it, or at least update your mind. So, and we're going to have time to discuss this. That's it. Any questions, comments? Yeah. Should be by this weekend. Yeah, I'll check today. Should be done by this weekend. Yeah. Okay, so let's move on. So we ended up talking about learning theory, and basically the goal that we had in doing it was to explain why learning works. So basically what we said is one key assumption is that training distribution is the same as test distribution. And it was important also to make no distributional assumptions, although the learning is going to work even if you do make distributional assumptions. And then the key result that we had was that we understand generalization bound and what they depend on. And basically, we gave a result that looks like this, that this is the training error, what you see, the observed error that you see on the training data. And the error that you'll see in the future is related to it in the following way. There is some additional component that really depends on the VC dimension of the hypothesis space, or the size of the hypothesis space. And the reason this is important is really it affects model selection. It affects what hypothesis space do you want to use when you learn. And the type of graphs that we've seen, this is a version of something that we've already seen, is that you have training error goes up as the hypothesis, the x-axis, becomes more and more expressive. What you see here is, think about it as nested spaces of functions of hypothesis space. You start with H1, which is simple, goes to H2, which is a more expressive class of function. H3 is even more expressive class of function. And as this goes up, your training error is going to go down. At the same time, you expect that your test error is going to go up because you have a lot more flexibility in which hypothesis to choose. And therefore, you can overfeed the data. And we want to be somewhere in the middle. And this is expressed by this trade-off. So that's basically what we talked about. This is also called the principle of structural risk minimization. Risk coming from the term that we called minimizing the empirical error. So that's one key result. However, we want to do more than that. And it turns out that actually we can use this to drive algorithmic frameworks that are important. Yes?
What does COLT stand for, C-O-L-T?
COLT stands for computational learning theory. Okay? Okay, so the way we presented it, VC dimension is basically just a combinatorial parameter associated with the class of functions. And for example, if we take the case of linear functions, we know that it has low VC dimension, so it's good to learn linear functions, better to learn linear functions than, say, high-degree polynomial functions. However, the next step, that is using this algorithmically, or using these ideas algorithmically, really depends on refining this notion even further to make it not only dependent on the class of functions, but also on the data set that you'll see. And really the intuition comes from this example that we've seen before, right? So here you have the same data set, blue and red points, and I separate them using two distinct H's. And we all agreed that one of them is going to be better than the other. We all liked H2, the one on your right, better than H1. Both of them are linear functions, so the standard theory of VC dimension isn't explaining it. And really what we want is we want to move to a VC dimension theory that is data dependent. Specifically here, we want maybe to use the margin within which we separate the data points as one of the parameters. So this is what we had here. So in both cases, H1 and H2, the error is 0. The empirical error is 0 in the graphs that I showed here. The VC dimension is 3 in both cases, so we don't have tools to distinguish and say that we like H2 better than we like H1. So how do we explain this intuition? So the explanation is going to come through the intuition that you all had, which is the separation is better in H2. So the closest point to the hyperplane in H2 have a larger distance than the closest points to the hyperplane in H1, in the H1 case. Right? So we're looking at the closest points, and we ask which one are farther from the hyperplane, and that gives us some idea of robustness. So to formalize this exactly, we are going to introduce the notion of margin, which we already saw before, but let's just formulate it. So the margin, gamma I of a point xi, with respect to a linear classifier, which I'm writing here as dot product wx plus b, is defined as the distance of xi from the hyperplane. You've seen this in homework 0. The distance is this dot product divided by the size of w, absolute value. So that's the margin of a given point. And now when I have a set of points, basically what I'm going to do is I'm going to do minimum over all the elements in the data sets. The margin of a set of points with respect to a hyperplane is the margin of the points closest to the hyperplane. Okay, so now this is going to allow me to refine this notion of VC dimension, because I'm going to define, instead of just the class of linear functions, I'm going to define the class of linear function that separate the data with a given margin. So this is a well-defined thing. So you give me a margin. I can talk about all those linear functions that separate this data set with a specific margin. And this is going to be a smaller class of linear functions and parameterized by this margin. And you can also see that the number of functions, if you want, or the complexity of the class of functions that separate with a large margin is smaller than those that separate, with a high margin is smaller than those that separate with a small margin. So let's just define this. So let H gamma be the space of all linear classifiers that separate the training data with a margin gamma. So this is a new class of functions. And then it turns out that one can prove that the VC dimension of this is a function of R squared divided by gamma squared, mean between this and n, plus 1, where, as we've seen before, so this is a term that you've seen before. R is the radius of the smallest sphere that contains all the data, and gamma is the margin. Where have you seen this before? Perceptron. So magically, the mistake bound perceptron comes back here and really shows that this kind of R square over gamma square, or something that depends, inversely proportional to gamma square, is really important. It really indicates something about the complexity of the class of functions that we deal with. So we're not going to prove this theorem, but hopefully the intuition is clear. So the largest the margin, the smaller the class of function that can do it. So you can just plug this into the bound that we discussed before, replace the VC dimension with this, and basically what we get is we get an error bound or generalization bound for the space of all linear classifiers that separate the data with margin gamma. Okay, so that's the theory, and now how does it help? Basically, this observation is going to guide us toward which linear classifiers do we want to learn. Not just any linear classifier that separates the data, but rather we want to consider those linear classifiers that separate the data with a large margin. So the first observation we're making is large margin is good because it indicates small VC dimension. So our goal should be to find a separating hyperplane that maximizes the margin of a given set of examples. Make sense? Now, of course, there's a question of how should we do it. So the goal is clear. Don't just choose any linear classifier. Choose one that maximizes the data. We should think about how to accomplish this algorithmically. And again, this is the intuition. And the second observation is going to lead to an algorithmic approach. And the second observation is that if you make sure that the size of W is small, it's going to result in a large margin. So given the first observation, with the second observation, we're going to have an algorithmic approach. We're going to try to minimize the size of W. Now, here you can say, well, something is wrong here. What does it mean, reduce the size of W? You should complain here. Why? Yeah?
Are you just reducing the magnitude of the vector?
So what's wrong with that?
Well, like, it could be a unit vector, but like, I don't see the difference between a unit vector and multiplying it by like unit vector times 10, right?
Right. So, exactly. So you would say, you know, if W separates the data, 3W also separates the data, and 1 over 17W also separates the data. So what are you doing here? So that's an important complaint. Before we get to deal with this complaint, just summarizing what I said before, that this gives me an algorithm, right? For among all those W's that agree with the data, I want to find the one that minimizes W, and then comes your complaint, which is justified. And in order to address it, we really need to better understand the relation between W and the margin. So that's what we're going to try to do now. So here is the picture that we have in mind. And basically, the observation that you've made is that a hypothesis has many names. When I say that W separates the data, there are infinitely many things that look this way, that geometrically are behaving this way, but they have many, many names, right? So what should we do? I'm just keeping here the distance between a point and a hyperplane, so we'll keep this in mind. Even though in my discussion now, I'm not going to carry the B with me. You already know that we don't have to carry the B with us. It's going to be a little bit simpler. So we need to introduce a notion of maximal margin. Before we talked about margin, now I'm going to talk about maximal margin. So the maximal margin of a data set S is defined as follows. So I have max and min here. So let's understand what it says. So I'm looking at the minimum over examples, x comma y, of y dot product wx. Right? So remember that this product inside the absolute value is positive if it's on the right side of the data set, if the examples are predicted correctly. Otherwise, it's negative. And once I chose the point that satisfies the minimum, which is the closest point to the hyperplane, then I'm going to take max over all these W's, but I'm only going to consider those W with size 1. So I already said that I have many, many names for each W. For each W, I'm going to choose now one representative, the one that has size 1. Right? So think about all these W's as being split into equivalence classes. I change the angle, I change the W. But for a given angle, I can multiply it by 7, by 17, by 2. Among all these, I'm choosing only one representative, the one that has size 1. So here is, in words, what I've just said. For a given W, first find the closest point. That's a well-defined geometric notion, the closest points to the hyperplane. Then, across all the W's, but only those that have size 1, because I'm taking one representative from each infinite collection of W's, find the point for which this point is the furthest. The minimal point is the furthest from the line. Right? So think about this H1 and H2 example here. So first of all, I found this red point that is the closest to the line. And then I found the red point here, which is the closest to the line. And from among these two, I chose this one because its distance to its line is farthest. Yes?
In the second point, we write then across all W's find the point for which this point is the farthest. Shouldn't we say across all W's find the W for which this point is the farthest?
Yeah. So that's exactly what we're doing. It's max over W's of the mean. So for each W, let's assume there are 7 W here. There are infinitely many, but let's assume there are 7. For each one, I'm choosing the closest point. And then I'm looking at the physical distance of this closest point from each one of the W's, and I'm choosing the W for which this closest point has the largest distance. So here it's mean over points, and this is max over W's. So I'm choosing the distance that corresponds to the good W. Yes?
Then shouldn't it say for number 2, then across all W's decide to find the W for which the point distance?
So really what I care about, the way I've written it here, I care about the distance because I care about the max margin. But in a few seconds, I will also care about the W. Here I care about which is the distance that maximizes because I define max margin. And then I will care about which W produces this distance. Yes?
So we have different scaled versions of W.
Yes.
So we can just normalize that W and consider.
That's what I'm doing here, right? So I'm normalizing, I'm basically choosing one of these W's.
You can choose any W and normalize that W.
Same thing, right? So one of these W's, so I have a lot of W's that have the same angle. One of them has size 7, one of them has size 2, one of them has size 0.01. One of them also has size 1. I'm choosing this one. It's kind of like normalizing them, right? So basically, think about it this way. There is a notion of a geometric distance. This is the one I care about. I don't care about multiplying W's by some number. The notion of the geometric distance is a well-defined thing. Okay, so I talked about the margin, the max margin. And now, what is the hypothesis that I'm going to choose? I'm going to choose the one that is the argmax over all W's, right? So here I chose max of the distance. So this gave me the margin, and here I'm choosing argmax, which is the W that does that. And this is going to be my hypothesis. Okay, so that's the first interpretation of what we are doing here. The first interpretation is among all the W's of size 1, choose the one that maximizes the margin. That's what we want to do algorithmically. So let's keep this interpretation and do a recap of what we are doing here. We're going to come up with another interpretation. So we have a theorem, the theorem that really motivates what we want to do. The theorem says, if H gamma is the space of all linear classifiers that separates the training data with margin at least gamma, its VC dimension is bounded with something that is 1 over gamma squared. And this first observations tells us try to maximize the margin. The second observation is if you have a small W, it's going to lead to a large margin, which means that the algorithm should be from among all those W's that separate the data, find the one with the minimal size W. So we're going to put these two observations together to an algorithm, as we said. you're going to believe the first theorem. I'm not going to prove it, but I will justify the second observation because it's very important for us to really understand this relation between size of W and large margin. So the proof will actually allow you to play with it. So let's do this. So how do I move from margin to size of W? Yes?
Is the VC dimension always an integer? Like,
The VC dimension is an integer, yes.
so, but on the previous slide when it said R squared over gamma squared, that's...
It's less than, yeah. Yeah? So that's the way it's written. Okay, so I wanna understand the relation between the margin and the size of W. In order to do it, I'm gonna define this W star. W star is exactly what you've seen before, argmax over all W's of size 1 of the minimal distance point. So it's the W that give me the max margin. And again, I'm just showing that there are two steps here. There's the step of find the closest point, and among all the closest point, find the W for which this closest point is the farthest. How do we find this W star? I'm going to define the following optimization problem. The following optimization problem defines W0 as argmin of the size of W square. It's easier to work here with the square. The W that separates the data with margin 1. So what does it say? Consider all the W's that separate the data with margin 1, right? So Y times dot product WX is greater or equal to 1. Consider all these W's. Take the argmin there. Call this W0. Okay, well defined. And now my claim is that W0 normalized is what I need. W0 normalized is exactly W star. So again, the normalization of this W0 is the largest margin separating hyperplane. So basically what I did is I said, that's what we want this W star. Here is a procedure to get W star, solve this optimization problem, compute W0, its normalized version is going to give you W star. Why is that true? Okay, so that first of all gives us the second interpretation. The first interpretation was the max margin, the W star. The second interpretation is among all the W's that separate the data with margin 1, choose the one that has the minimal size. This will be our algorithmic approach, yes?
Is one just choosing arbitrarily here?
Yes, yeah, could have done 7. But I have to have a fixed number, yeah. Okay, so why is this true? So let's just do a little bit of algebra, and hopefully this will give us also some intuition for the relation between W and margin. So the next slide is devoted to showing that these two interpretations, the W star one that says it's the max margin, and the W0 one that says it's the minimal size, that these two are the same thing. How do we show this? So the claim is what I just says, that if W0 is defined to be the solution of this optimization problem, the one that is the smallest size among all W's that separate the data with margin 1, then its normalized version is the max margin W. Why is that true? To show that it's true, I'm going to define W prime to be W0 divided by size of W0, which is the normalized version of W0. W star, as we defined in the previous slide, is the largest margin separating hyperplane. that has size 1, and I want to show that W prime is equal to W star. Okay, so first of all, I want to argue that W star divided by the margin satisfies this condition. What does it mean? That W star divided by gamma is one of the W's considered here. Okay? Why do I know that? Because what was W star? W star separated the data with margin gamma. So W star divided by gamma separates the data with margin 1. And therefore, it's one of these W's considered in this argmin condition, the 2-star condition. And because it's considered there, W0 is less than it, because W0 is the minimum one in this sense. So W0 size is less than the size of W star divided by the margin. This is just by the definition of W0 being the smallest one there. And I'm also claiming that the size is 1 over the margin. And this is directly from the definition of W star that has size 1. Okay, so that's one step. Now, I'm arguing that for all data points in S, let's consider our W prime, right? Remember, how do we define W prime? To be this normalized version of this W0. So why W star dot product with X? I'm just plugging in our W star. It's the W0 normalized. I'm arguing that this is just the definition, and by the definition of W0, it's greater than 1 over W0, right? Because W0 separates the data with size 1, and therefore, this one is greater than 1, so I get that all this fraction is greater than 1 over the size of W0, and therefore it's greater than the margin. So basically, this is just the definition of W0, and this is what we proved here, right? We proved that the size of W0 is less than 1 over gamma, and therefore 1 over W0 is greater than gamma. So what have we shown? We've shown that W prime, which is defined to be the normalized version of W0, satisfy our constraints, and its size is 1, which implies that it's the largest margin of size 1, so W prime is exactly W star. Let me summarize what we've done. We said this is really the way our algorithm is going to work, right? So we're going to try to find this W of the smallest size that separates the data by some large margin, margin 1. We want to argue that this one is the max margin, because the previous slide we said we are looking for the max margin W. What we've shown is exactly that, right? So we've shown that this W prime that we define is exactly this W star. So basically we show that interpretation 1 and interpretation 2 are the same interpretation. If you want to find the max margin, try to minimize the size of W. So let's just take some examples here and convince ourselves that that's the right thing to do. So in this slide, I'm adding the B. So you'll see it in both ways. What do we see in this slide? So what is H1? H1 is the hypothesis Wx plus B equals 0. So the positive point here I'm showing it here with these arrows. The positive points are exactly those points that satisfy wx plus b equal plus 1. The negative points, the blue ones, are those that satisfy wx plus b equal minus 1. And the hyperplane itself are the set of all points x such that wx plus b equal to 0. So that's what it means to be a separating hyperplane, and that's what it means to be the closest point to a hyperplane that separates the points with a margin 1. Right? It basically means that the positive points are sitting on the equal minus 1, and the positive points are sitting on the equal plus 1 line. In all these cases, I'm assuming that the data is linearly separable, right? So this is the picture here. So what is the distance now between the positive points and the line, or the negative points and the line? Because we're talking about points that are on wx plus b equal 1 and wx plus b equal minus 1, the distance between the point, the closest point, and the separating hyperplane is just 1 over the size of w. Everyone can see this? So what is the distance between the positive point and the negative point, or the closest positive to the closest negative, is 2 over the side of w. So that's really is the thickness of the hyperplane that we have. So what have we done here? We looked at all w's of different angles. We scaled w, right? We said we're going to normalize it, or we're going to choose one representative that has size 1, such that the constraints are tight. What do I mean by the constraints are tight? That the examples are, the closest example are on the plus minus 1 line. So if I multiply the w by 7, now the same points that have the same geometrical distance are going to be on wx plus t equals 7. I scaled everything so they're going to be exactly on the wx plus t equal plus 1 and minus 1. That's what I mean by the constraints are tight. And now when I do this for all the w's that I have, example here, this one case and second case, now I'm choosing the one with the minimal size, which is the largest margin. Questions? So I'm sure you all have a lot of questions. This is something you have to play with a lot, yes?
So the size of the margin depends on the orientation of the plane, right?
True.
But this is saying that if you scale down w by a constant scalar, if the margin gets bigger?
No. It's exactly what you said first. So I have here two h's, h1 and h2. For each one of them, I choose one representative, which is the one of size 1. Now, I'm looking at the size. So here is an example. So I worked out for you an example. You will go over this example and invent your own. And let's just work out the details and see what happens here. So what is this line here? So I'm talking here about this hypothesis. The hypothesis that I have here is going to separate these 4 points. I have 2 negative points, minus 1, 1, and 0, 0 are negative. 1, 1, and 2, 0, the red ones, are positive. This is one separating hyperplane. It's this plane. It's the plane, the line, because we're on the two-dimensional plane, the line is x plus y minus 1 equals 0. Everyone agrees that that's the line x plus y minus 1 equals 0? It goes through the point 1, 0, 0, 1. So it's this line, x plus y minus 1. If I want to write it as a WB representation, which you want to make sure you can, then W is 1, 1. B is minus 1. Okay? You should agree with me on that. That's just, middle school or high school geometry. Now, let's see what else do we care about here. So you can think about the distance from one of the points. Let's take the positive point 1, 1 plus this red point here to the line. Right? We can compute the distance. Here is, I'm doing it here. So the distance is going to be the dot product 1, 1 with 1, 1. 1, 1 is the point. And 1, 1 is also my W here. So it's Wx minus B divided by the size of W. This is my W, 1, 1. So I get 1 over square root of 2, which happens to be what I promised it will be, 1 over the size of W. Okay? So that's one case. Now, let's assume that I'm taking this line and representing it differently. So exactly the same line, x plus y minus 1 equals 0, I can also represent as 2x plus 2y minus 2 equals 0. Agreed? Same line. So geometrically, everything looks the same, but w now is 2, 2, and b now is minus 2. I can also do the same thing, right? I can compute the distance. So the plus plane, by the plus plane, I mean the plane on which the closest positive points reside. Now the plus plane is going to be wx plus b equal 2. How do I know this? I know the slope. I know a point that is going to be there. I can substitute and solve, and I can figure out what is this plane. So basically, this kind of gives me an understanding of what happens with this plane, or with this line in this case, and the two different names that it can have. Now, this is not the only line that separates these two red points from these two blue points, right? Here's another one. This vertical line here also separates them. Do you see that? This vertical line that goes here. What is the name of this vertical line? It's W equal 1, 0, because it's vertical. And I put B to be at 0.5 here, right? The middle between the origin and 1, 0. So this line is this line. It's W equal 1, 0, B equal negative half. So now I can do exactly the same thing for this line. So let's do this. For the second plane, which is W equal 1, 0, B equal negative half, let's take, again, the positive point 1, 1, and see what happens, right? So basically what I'm going to do is I'm going to see what is the line on which the positive points, the closest positive point reside. I'm computing it this way. So it's this 1, 1 plus is going to give me 1, 0. This is my W times 1, 1 minus a half. It gives me a half. Not good, right? Because now the positive points are residing on have margin a half. I want to scale everything so that the closest points have margin 1, right? Because I want to have unique names for the W. So I'm scaling everything so that the positive points have, the closest points have margin 1. So I'm going to double it, right? I'm going to do something so that this is going to give me 1. What should I do? Let's solve, right? So I'm going to scale WB. How do I decide how to scale? I'm going to scale by C, by a constant C. So the line, instead of being 1, 0, is going to be C0, C0, dot product with my point 1, 1, minus, I scale the B also, minus C over 2 is going to give me 1, right? That's what I want. I want the positive points, the closest positive point, to have margin 1. So let's solve for C. When I solve here for C, I get that C is equal to, you could have guessed that. So really, I have to rename this line. I'm not going to call it anymore the line 1, 0, negative a half. I'm going to call it 2, 0, minus 1. Okay? I just rescaled it. Again, how did I choose what to rescale? I want the margin to be 1. So now I can take all my points and see what happens, right? So I can compute basically all these dot products. And it's true. These 2 points now that are closest to the line, this point 0, 0 and point 1, 1, are going to give me 1 and minus 1 respectively. And you can see that indeed this point and this point, the origin, are the closest to this vertical line. And the other 2 points are farther away. So I did the mean part of my max mean, and I got 1. I don't care about these 2 points because they are farther from my hyperplane. So now I'm happy. So I found the closest points to the hyperplane. Now let's see what do I get when I work with this mean. So remember that I had inside I had a mean, find the closest points, and then look at the distance of this closest point and see if you like this hyperplane. What is the distance? The distance now, or the size of W, is going to give me 2, right? Because I had to rescale in order to place them at 1. So my W now is 2, 0. The size of W now is 2. The size of W there was better, right? Before we had W square root of 2. Where was it? Somewhere here. So I prefer this W over the vertical W. That's the algorithm, basically. So again, what did I do? I had the 4 points. I had 2 W that were candidates. And basically, I showed you that I can choose a representative. I have many options, but I choose the one that places the closest points at margin 1. Here, I just got it for free. I chose it and it worked. Here, I had to rescale it to get the right representative. And once I had that, I could look at the size of W and decide which of these hyperplane is going to be the better separator. And I chose this one over the vertical one. Yeah.
In this example, like on the left slide, when we are scaling W, we are also scaling B.
Yes.
So in my mind, B was always a part of W. In that case, when we are considering the size of W, shouldn't we also take B into account and shouldn't it be rooted into?
Okay. Good point. I'll get back to it. So that's why in the previous slides I hit B, and I decided that we are working on this n+1 extension, and then we carry B with us, which is the right way and the simplest way to do it. So here I just did it with all the details, so you'll see that I'm also scaling B. As I get to the optimization problem that drives SVM, you'll see that there's a little bit of cheating there. Really, you should actually include B in W, and people don't. So if you go to the software packages, they don't, and it's not exactly the same, but it's almost the same.
They don't include B in the size of W?
They don't, no. So they, when I'll show you in a second. But basically, what we do here is the right thing. I mean, B has to be part of W.
It should also be a part of W
when we compute the size,
but
yes.
wouldn't that make things wrong? I mean, in certain situations, if we don't include it?
Yes. So there is a little bit of inaccuracy in the way this works. So really, the best way to think about it is fold the B into the W and work in the n+1 dimensional space, yes. But yes, so forget this discussion for a second. We're going to go back to it. My goal here was that, I mean, it's a complex thing, right? So you have to understand that there's a notion of geometric margin, which is the important one, geometric distance, and the size doesn't matter there, really, right? So that's why we choose one representative, and we have to define what representative we choose. And the goal of this example, and please work out yourself, the example is to basically illustrate that. This example is completely equivalent to this example, only that I gave all the details, and it's completely equivalent to what we said here, which is the relation between the max margin and the minimal size W. These are the same thing. And hopefully this example illustrates that. And again, I suggest you just invent your own example and work it out. Questions on that? Okay, so now that we know what we're after, we can formulate the SVM problem. So we show that the sought-after weight vector is the solution of this optimization problem. Minimize the size of W. I'm minimizing half the size. Doesn't matter, it's the same thing. Such that all the points are separated by margin at least one from the hyperplane. Okay, that's what we showed before. So this is a quadratic optimization problem. We have n plus 1 variables because I put the B into my W. And I have each example defines the constraints, right? So each example here defines these constraints. It has a unique solution. The problem is done. So just saying it now with the B, I want to minimize the size of W such that yi times dot product Wx plus B is greater or equal to 1. And again, what is the margin here? We already computed this before. The linear separator is Wx plus B equals 0. The distance, the thickness, if you want, the distance between the closest positive and the closest negative is 2 over size of W. And this is what we want to minimize. So maximizing 2 over W, which is maximizing the margin, is equal to minimizing the size of W. Okay, so this is what is called support vector machine. The reason it's called support vector machine is because W star, the one we care about, is supported by the examples that are exactly distance 1 over size of W from the separating hyperplane. These are the points that really define the W. Points that are farther away, we don't care about them. They don't really define the W. You can go back to the example that I showed before when, with the vertical line, you saw the 2 points are important, and 2 points were too far, and we didn't really care about them. They did not define the W. So here, what I circle here are the closest points to the hyperplane, and they define the W. So that's one way to think about it. Another way to think about it is through the following theorem that says, let W prime be the minimizer of the SVM optimization problem, the one we're after. Define I to be the set of all points, that's the set of indices of the points that are exactly on the boundaries, the set of all xi such that W star dot product xi is equal to 1. And then we can say that there exist coefficients alpha, positive alphas, such that W star is completely defined as a linear combination of these xi. So W star is the linear sum of alpha I, yi, xi. So that means 2 things. It means that those xi's that are not satisfying this, that are farther away, these blue points here and these red points here, they don't matter, right? So they are not defining W star. W star really is defined by those that are on the boundaries. That's why they're called support vectors, and this is called support vector machine. Now, this representation here should ring a bell. You've seen it. Where have you seen it before? The dual space, when we talked about perceptron. What did we show for perceptron? What was the W there?
Linear combination of the examples on which we get tested.
Right. So it's very interesting. So both of them are dual representations in the sense that W is defined as a linear combination of examples. And the examples themselves are different, but you can see that they are actually very, very related. So before we had W defined as a linear combination of all examples over which we made mistakes in the past. If the example was too easy, we don't care about it. It doesn't help to define W. And now, in exactly the same fashion, W is a linear combination of all those examples that are closest. And these examples that are farther, and again, they are too easy, we don't care about them. They don't serve to define W. So it's really very, very close, for a reason, a very close concept. So basically, this property is shown. I'm not proving this theorem, even though it's not too difficult, but basically it's shown by moving to the dual problem that we talked about before, and I'm just formulating it here, right? So the theorem says if W star is the minimizers and I is this set of points, then there exist coefficients that are positive that satisfy this. Okay, so here is the footnote that addresses your question. We can always augment the vectors by adding one dimension, forget the B, and in this case I denote this as X hat and W hat. If I do this, then the SVM problem becomes, this is the SVM problem the way I formulated it, right? The top one here, minimize norm of W such that the constraints are satisfied. Now, if you open it and unfold B, you see that really you have to minimize this plus B squared. And we don't. So there is a little bit of inconsistency here. Doesn't change a lot, but good to realize it. Okay, so so what have we done so far? I mean, we talked about SVM. Now, it used to be that computing SVM, so learning, was a very time-consuming thing until at least maybe 10 years ago, or less than 10 years ago even. Basically, the idea was to solve a quadratic program, which is NP-hard and really expensive. No one is using this anymore. Modern methods are using stochastic gradient descent methods, coordinate descent methods, dual coordinate method, which computes in the dual space. They are much, much faster. So that's one important thing. So today, if you run SVM, it's actually quite efficient. Another question to ask is, I kind of convinced you, at least I was trying to convince you, that max margin is the right thing to do. Makes a lot of sense. And intuitively, it is the right thing to do, but is it optimal? Is the objective function that we are optimizing the right one? And it's very easy to see that it's not. So here is just a plot that I show from some, one of the problems that we talked about earlier in the class, context-sensitive spelling, 17,000 dimensional space, and I show you a histogram of the distance of points from the hyperplane. What you can see is two things. First of all, it's not symmetric. It's continuous, right? So there's really no separation. Where should we put the hyperplane here? It's not completely clear. And what is completely clear, though, is that wherever you put it, you're going to make some mistakes. And you want to ask the question of, do I really want 1 point or 2 points to dictate where I'm putting the hyperplane, right? So imagine that you have a more extreme case than this. All the positive points are here. All the negative points are here, with one exception. One of them is here. if I really want to optimize the SVM, the hard SVM objective that I show, I have to put the line here so that all the negative are on one side, all the positive are on one side. But probably it doesn't make sense. It makes more sense to disregard this extreme negative point and be in the middle from the majority of the points. So just maximizing margin, which is a good principle for all the theoretical reasons we gave, is probably not always the right thing to do, right? So I don't want to depend on extreme points. And one way to avoid this is to introduce the notion of a soft support vector machine, right? So a natural relaxation is maximize the margin while minimizing the number of examples that violate the margin, right? So that makes sense. So minimize the number of positive points that move to the other side, negative points that move to that other side. This is hard to optimize. So instead, what we're going to do is we're going to, just like we did throughout the semester, we are going to move to a surrogate objective that is convex, that we can optimize. And the way we're going to do it is we're going to introduce this notion of a slack variable. So instead of using these constraints, right, so I want the xi's to satisfy that y dot product wxi to be greater than 1, I'm going to say, well, not greater than 1, maybe greater than 1 minus something positive. This is going to be my slack variable. So I'm relaxing it a little bit. So this psi I is going to be defined per example, and I'm going to relax my requirement. That means that now what I want to do is I want to solve this problem. These are the set of constraints I want to satisfy, right? So that's what, before I had all the way until here, now I'm adding this slack variable that is positive, and I want to minimize the size of W plus the size of the xi's, or C times the size of the xi. So what is the role of C here? What happens if C is very, very large? That? It's less soft, which means I really care about, I don't want the xi to be there, right? If C is very large, I really want the xi to be 0, right? I don't want to give you slack, right? So if C is large, it means I really care about small training error, no slacks, at the expense of the margin. If C is small, then I'm allowing you to have some slack, and hopefully this will reflect better on the true error eventually. So it gives me some softness in this optimization problem. So now this is the problem that we want to solve, and I want to rewrite it a little bit. So look at the constraints that I have here. I'm going to rewrite it instead of this dot product greater than 1 minus xi. I'm going to define it as xi greater than 1 minus the dot product. And hopefully, you can see that because xi is positive, really, xi is defined as the maximum between 0 and 1 minus this yi dot product. And you've seen this before. This was the hinge loss. So really, what I'm doing now is I'm going back to optimizing this blue function here, which we call the hinge loss. And now I can write this way. So I have minimized the size of W plus C times this pointwise hinge loss. What is the interpretation? Really, it's something that we've seen before, right? So we have a component. Before we've seen it reversed. On the left side, we saw this part, which really you can think about the error, the empirical error, right? And then we added the regularization. Now I'm just writing it differently because, you know, this is kind of the natural way to write it when you think about SVM, but it's really the same function and the same sum of components that we've seen before. right? So the problem we solve is this. I'm just summarizing what we've done before. This is the soft objective function of SVM. And I basically want to remind us that we actually saw this before, right? We have a component that is the empirical loss, a component that is the regularization term. You can choose to replace the empirical loss by something else. You can choose to replace the regularization term by something else. And all of them basically have the same kind of conceptual thing. So this really turns out to be a general form of a learning algorithm. Minimize the sum or weighted sum, because we have this C in the middle of these two components. Questions? Yeah.
The hard SVM would not have a corresponding similar representation in the Hind's law sort of thing.
No. So the hard is, we have 0 here, right? So basically, in the hard, this is 0, and we add instead hard constraints. You have to be outside the boundaries of 1. Okay, so just as an example, so you can think about this case. This is one extreme case where what I have here is I have an overfitting classifier. So I really wanted not to make mistakes on the left side on the training data, right? So I chose a very narrow hyperplane, the thick, and then I'm paying for it a little bit because I make mistakes on the test data. The other option would be to try to separate the data with a thick separator. So you can see that I made some mistakes here. And hopefully the generalization here is going to be better. So that's kind of the game that we're playing. And it's, again, going back to the same underfitting, overfitting, bias variance picture that we've seen before. So you have simple models that have high bias and low variance. You have complex models that have low bias, which means low empirical error, but high variance, and you want to be somewhere in the middle. So larger C means that I want to have a low bias. It means I care about this psi, right? So let's go back to see it here. Larger C means that I want this psi to be very, very small, or 0, right? So I care about my bias. I want to have low empirical error during training. And if I have small c, then I'm allowing you to have error, observed error, and I'm hoping that this will support better generalization. Okay, so as I said, I can replace the regularization function. I can replace the way I measure the empirical error. And even with SVM, there are multiple versions, right? So we talked about this SVM, the minimal the objective function here in the middle, right? So this was the hinge loss, and this was the regularization parameter. It's also called L1 loss SVM. You can also have another version of SVM that is called the L2 loss, where basically you take the square of this hinge loss. And again, you can see that this has the same form. You can replace, as I said, the way you measure your error with this log loss. This function is going to be called logistic regression, and we're going to justify it in a couple of weeks from completely different perspective. It's going to be an outcome of a relaxation of a very simple probabilistic learning algorithm, but really very interesting to see that it really has the same form. So this kind of is going to close the circle. Okay, so I'm not going to spend a lot of time on computation because you're never going to program it. You're going to use a package. I already said that it used to be very hard. Now it's very easy. The way people optimize is still changing. Some people still try to improve optimization methods for SVM. Basically, people are using versions of gradient descent in the primal or in the dual. Today, in the dual is a more popular way of doing it. And I have a few slides here that describe how to do stochastic gradient descent for SVM. And if you go even more into the slides, I'm not going to go into it. Okay. There are about 20 slides about theory of optimization if you want to refresh your memory about this. I'm not going to say anything about it. I just want to say one other thing. We talked about kernels. Kernels really became popular in the context of SVM, even though it's much simpler, I think, to understand what they do in the context of perceptron, which is what we did a couple of weeks ago. So I just want to show how this looks here. So if we are working in the primal is the standard way, then when you want to work in a higher dimensional space, you're going to transform your xi to a higher dimensional space by introducing this phi. So everything is going to be exactly the same, only that the dot product are going to be yi, w, phi of xi. Same thing, same algorithm. And you can run SVM this way. If you want to work in the dual space, which was the original intention, when you blow up the feature space, things become a little bit more complicated. The way this is going to be written is this way. So the optimization problem becomes this, where alphas are these coefficients that we've seen before for the dual representation, and Q is this kernel matrix that I'm writing here. The problem is exactly the same problem. So if W star is the minimizer, then you can write it as a linear function of the examples. And in the case of blowing up the feature space, it's going to be the linear function of the phi of the xi. So I'm not going to show how to derive the dual form here with the kernel. There's a little bit algebra, and I think it's written in one of the hidden slides. If you want to go over it, feel free to go over it. Questions?
What is the E transpose alpha? What is the E?
Oh, this is just E is E, the natural log. And sorry. This is the unit matrix. Yeah, shouldn't have been E. Yeah. So basically, it's yeah. So this is the kernel matrix. This is the vector of the alphas that we have here, and this is basically just making it a matrix because this is a matrix. So you take the alpha and make it a matrix, a diagonal matrix. Okay. So as I said, there is a lot of optimization stuff in the rest of this, which I'm not going to go into. You don't really need to know it. I assume that most of you have seen some of it. If not, you can refresh your memory there. Questions? No questions. Okay. So as I said, next week we're going to do neural networks. Someone else will replace me because I'll be out of town next week. And I'm going to see you in 10 days or so.
I just want to I can take it.
1:30. Come to my office. We'll have you sit in the conference room in that. Yeah, yeah.
Thank you. I really
Sure.
appreciate it.
Hi, Dr. Rose. I am Sidong, so do you have time today to talk about the homework?
No,
Oh, I need to
I'm
wait.
sorry. It will have to be just after I'm back. Yeah, yeah. So what's your name, Iman?
Zitong.
Yes, okay. Yeah, so we'll talk once I'm back, which is going to be the Monday,
Next Monday.
next Monday.
So
Yes.
can you tell me a little about
So the problem is that we see similarities between your homework and other homework. So I wanna discuss this with you. I think it's November 11, where when we can meet.
Thank you.